We're live at the moment. And I'm going to be hitting our countdown here in just a couple seconds.
All right.
It just lets the system kind of catch up a little bit before we hit the countdown, then everything is running. Hello, good afternoon, everyone. It is my pleasure to introduce you Michelle Henley, President of TMG Frontline Solutions. She will be giving insight into break the reactive cycle with defect elimination. Thank you very much, Michelle. It's all yours.
Thank you so much. Let me jump right in. I'll be talking today about how to use defect elimination to break the reactive cycle. And I want to start off by talking about some of the big ideas in reliability. Reliability is nothing new. I've actually been attending conferences about it for over 25 years now. And while there are always a few new techniques and technologies, most of the big ideas of reliability have been around not just for years, but actually for decades. In fact, many of them don't just predate my career in the industry, they actually predate me being on the planet. The term reliability actually came into common usage in the 40s and 50s with the new machines and technologies of World War II. This is when thermal imaging and ultrasound got their start. Weibull analysis dates from the 1960s. Nolan and Heap published their groundbreaking paper on reliability-centered maintenance in December of 1978. And even the term Internet of Things, which I think of as being very, very modern and hip and new, was actually used initially in 1999, so more than 20 years ago. The question we need to ask ourselves is, since these big ideas have been around for such a long time, why do so many organizations still struggle to break the reactive cycle? To break the reactive cycle, organizations need to get a handle on the defects that are impacting their equipment, as well as their processes and practices. So let me start off with my definition of defect. This is the one we've been using for the past 25 years with the manufacturing game. It's anything that erodes value, reduces production, compromises health, safety, or environmental performance, or creates waste. And at the manufacturing game, we represent these defects as bugs that are invading our system. From my experience, a key reason that organizations continue to struggle with the reactive mode is that they significantly underestimate the number of defects in their system, the sheer volume of defects. While most people see the big issues, they either fail to see or fail to recognize the significance of the loads and loads and loads of smaller ones. Most sites actually have a tsunami of bugs that no matter how hard they try, they just can't outrun. Now, when I mention defects, the first thing that most people think about are the defects that come from design. These are some of the more obvious ones. Examples would include things like a pump that's too small for the required flow, or maybe a refinery that was designed to run sweet crude, but because of changing economic conditions, they're now running a sour crude slate, and the equipment just wasn't designed to handle that. But this category also includes design issues that impact either operability or maintainability of the equipment. So a valve that's needed for normal operations that's 15 feet up in the air with no easy access, to me, would be a defect from design. Same thing if we have a sight glass that's obscured by other equipment, and it's something that a mechanic needs to be able to access on a regular basis to do their PMs, well, that would be a defect from design as well. But even with this broader definition of defects from design, there's still just one piece of a bigger puzzle. We also have defects that come in with our raw materials. Now, raw materials would include whatever your feedstock is for your particular product, but I also include in this category of raw materials anything else you need for production. So if you need process air or process water or packaging materials, those would be raw materials as well. So examples of defects from this category would be things like sand and water that are in the crude on an oil production platform. Might be wood chips that are in the rubber if we're talking about a tire manufacturer. Could be in a chemical plant, we have poisons to catalysts. And if we're talking about a mining operations, maybe it would be things like rocks that are too big for the equipment to handle. In addition to these defects from raw materials, we also put defects in our equipment based on how we run that equipment. And we call these defects from operational discipline. So examples would include cavitating a pump, maybe starting up a piece of equipment improperly, shutting it down improperly. Defects from operational discipline can actually come from a variety of reasons. So one possibility is that we just lack the operating skills that are needed within the organization. Maybe we have a very green workforce, we have high turnover, things like that. But we also might have defects because our training processes are inadequate. Or it could be a problem with our procedures. Maybe they're inadequate, they're incorrect, or just flat out missing. In addition to these defects coming from operations, we have defects that come from how we maintain the equipment. Examples would include improper alignment of a pump or using the wrong tool, maybe using a ratchet wrench when a torque wrench is needed. Just like the defects that come from operations, these defects could be from a basic lack of skills, could be inadequate training, could be problems with our procedures. But interestingly enough, one of the most common defects that we see in this category has nothing to do with the ability of the mechanics at all. Instead, it's that we put these mechanics into a reactive system, and that system emphasizes fixing things fast rather than fixing them correctly. So even the mechanic with the best skills, best procedures, best training can't do the job right if they're not given an adequate amount of time to do the job. Last category that we have for defects are defects from maintenance materials. These are our spare parts. We get parts from the vendor, and sometimes we get defects straight from the vendor. Some vendors have better quality than others, but we also have defects that come into our parts based on how we treat those parts after we've received them. So if we're transporting them improperly or storing them improperly, those would be defects from maintenance materials as well. So a couple of things that we see in this example are buying the cheapest parts, substandard parts, because they're the cheapest. Or one of the things that's been happening the last couple of years is we buy whatever's available, given the supply chain issues. We get what we get. Maybe it's not the best quality, but at least it's something. But again, we might get a part in that's perfectly good. Let's say we get belts in. If we're not storing them properly, protecting them from moisture, we're going to add defects to those parts. If we have a long shaft and as we're transporting it to the job site, we bend it because we don't have it supported properly, that would be a defect from maintenance materials as well. We would also include in here using the wrong type of part. So maybe we install a bearing and it has a C3 clearance, but C1 clearance is needed. So when thinking about defects, it's important to consider all of the sources of defects, not just the ones coming in from design. All right, so we've got defects pouring into our system, the big ones, the small ones, everything in between. They come into our system every day from a multitude of sources. And those defects accumulate in our equipment, which eventually leads to breakdowns. And the interesting thing about defects is that bugs by their nature are breeders. The more you have, the more you get. So think about this example. We have a piece of equipment that breaks, and maybe it's because we started it up improperly 6 months ago. Now it's actually failed, and so we have to repair it. In order to repair it, we have to bring mechanics in to work, and we have to use some parts to do the repair. So those are two new sources of defects that while we're fixing the original issue, we may actually be adding some more defects into the process that cause the next breakdown and the next one and the next one. And this is particularly true if this breakdown happens where we're now in a rush. We're trying to fix the equipment quickly because there's a lot of production pressure on us. Now, once the breakdowns start, organizations quickly realize there has to be a way to take defects out of the system. They naturally come in. We have to have a way of taking them out. This is where reactive maintenance comes in. So we put a drain there to try and drain off some of the defects to keep our equipment running. Now, waiting for failures before taking corrective action is definitely better than ignoring the failures, but it's a very inefficient way of doing the work. And on top of that, an incredibly frustrating way of doing the work. People get tired of fixing the same thing over and over and over again. So before long, it becomes pretty clear that we've got to do more about it. We can't just depend on reactive work. Now planned maintenance enters the conversation. And the thought is, we just need to drain the defects faster. If we build a system that can pull defects out quicker, then we're going to be in better shape. And to some degree, this is true. By looking for defects before the failure occurs, we're able to line up the right parts, the right people, the right tools. We're also able to coordinate with operations to make sure that we're taking equipment out of service when it's convenient for them, when there's a window of opportunity. All of this definitely makes this work more efficient at taking the defects out. It's definitely better than reactive, but there is a limit to how efficient you can get. You can only take defects out so fast. Something that's often overlooked is that the real leverage point in this system is to attack defects at their source. So instead of just focusing on the outflow and trying to take defects out faster, we also need to be looking at how do we prevent defects from getting into the system in the first place. Reducing the inflow of bugs slows down the accumulation rate, and this gives our planning and scheduling processes a fighting chance of keeping up with the amount of the work. Not putting defects in the first place also helps to eliminate this breeding effect that I talked about earlier, where we have more work, which introduces more bugs, which leads to more work, which introduces more bugs, and it continues. So making work go away is the essence of the defect elimination process that I'm talking about. And this is accomplished by reducing the defects coming in by eliminating them at their source. The easiest way for me to describe kind of the difference between planned work and defect elimination is with an example. So let me share this example with you. This was a refinery that we were working with, and they had a positioner on a control valve that failed frequently. And when it would fail, it would cause product quality problems. At some point, one of the planners said, we really need to get more efficient at how we're doing this work. And so the planner dug into the details and figured out that the failure was pretty consistently around 90 days. So armed with this information, he established a planned job that basically every 80 days or so, they would go in and replace the positioner. Because it was planned and scheduled, they could order the parts, they could line up the mechanics, they could figure out what day was the best day to take the equipment out of service. And so they could be much more efficient at doing this work. They also, by avoiding the failures, avoided the product quality problems. So they kind of lived with this solution for a couple of years, and it had certainly worked better than running to failure. But a cross-functional team that had gone through one of our manufacturing game workshops decided to take kind of a deeper look at this issue because they felt like a failure rate of 90 days was just too frequent. It didn't make sense to them. So the first thing they did was got in touch with the vendor to figure out what exactly was this positioner capable of. Their initial thought was maybe it was the wrong type of positioner. One of the things that they learned is that there was a maximum continuous operating temperature that this particular instrument could tolerate. Next thing they did was go out in the field to take a look at the positioner in its natural environment. And the first thing they noticed is that it was up against a hot oil line. And so they said, let's take a temperature reading and see if we're above the limit. And sure enough, they were above that continuous operating limit. So they realized at this point, we now know the source of the defect. It's the heat. That's why this instrument is failing more frequently than it should. And so they decided to eliminate this defect at its source by installing some insulation. So the picture on the right there, you can see the insulation around the hot oil lines to protect the instrument from the heat. So the site went from replacing the positioner after a failure and dealing with the quality problems to taking a planned approach where they would replace it every 80 days, to eliminating the need for replacing the positioner at all by eliminating the source of the defect. The last time I had talked to this facility, it had been over 3 years since the last time they had replaced the positioner. So this DE team was able to eliminate over a dozen replacement activities. So think about the amount of time and amount of money that would have been spent to replace this positioner at least 12 times in that same time period. So while the planned work was more efficient, the defect elimination work actually made some work go away. The other thing that this example demonstrates is one of the important characteristics of defect elimination, and that's that it promotes deeper questioning. So rather than fixing symptoms, defect elimination goes to the source of the defects. Let me share another example to talk about another one of the characteristics of defect elimination, and that's that big benefits can come from very small efforts. What I've seen in my experience is while most organizations at least do a decent job of tackling the really big defects, most groups are not very good at going after the small ones, either because they don't notice them or they think they're not important, or they just don't have time to get around to them. So in this example, there was a small group that would perform maintenance activities inside of different units, remotely located units up on the North Slope of Alaska. And to do their work, they needed electrical extension cords and they needed air lines. So they would drag these in with them to do their work, which of course created a potential tripping hazard. So to avoid the tripping hazard, they would secure these lines to either handrails or piping using zip ties or duct tape. So when they were done with their work, they would have to detach the lines. So they'd have to cut the zip ties and the duct tape. They would use either razor knives or snips, and sometimes they would cut the tie or the tape, and sometimes they'd accidentally cut a finger. So they'd have an injury situation. Sometimes they'd accidentally cut either the extension cord or the air line. And so they'd have to replace the damaged equipment. And so they had gone through a workshop. And again, they were taking that deeper approach of what's the source of the defect here? Is there something we can do about it? So one of the team members said, I just got a new laptop computer and it has an electrical cord on it. And that cord has a Velcro strap. And that, I can just use it to tie up the cord, and then I untie it and I retie it using the same strap each time. Maybe we could do something like that instead of using zip ties and duct tape. So this team went out and invested a whopping $9 to buy Velcro straps, and they started using them. They immediately noticed that the safety problems went away, no more cut fingers. They also eliminated all of the damage that they were doing to the lines. And so they were putting together this A4 form that you see here on the screen as a way of sharing their success with other people at their site. And they said, we probably are saving a little bit of money as well. Let's kind of add it up and see, because we were buying consumable products, zip ties and duct tape, and we have to throw that away. So we have to have trash bags. And so they looked into their history over the previous year, and they were stunned to find out that they were spending $25,000 a year on just stuff, zip ties and duct tape and trash bags. So by going with these $9 Velcro straps, they were able to reduce their operating costs by $25,000 a year. Now, while $25,000 maybe isn't a giant number, if you have everyone at a site working on these types of defects, that $25,000 over and over and over again adds up to substantial savings. So small efforts can yield some really big savings and sometimes some very, very surprising benefits. I'll share one additional example with you guys before I wrap up to talk about a final characteristic of defect elimination that I think is fairly important. Again, if you're focusing on these small projects, these small wins, that means a large number of people can actually get involved in the effort. And ultimately, this is what you need if you're going to change the culture. It's got to go beyond just the reliability folks or the maintenance department. So this story started a long, long time ago using the device that you see here on the screen. For anyone too young to recognize it, this is an overhead projector. You may have seen it in a museum somewhere. When I first started in reliability, this was actually a pretty high-tech piece of equipment. We didn't have LCD projectors or things like that to be able to share data directly from our computers. So I was working with a team that was working on a production problem that they were having. And the operations lead in the area, a man named Mickey, was spearheading the effort. And he had gone out to collect all of the data about the problem they were having. And he had painstakingly handwritten all this data on transparency film so that he could share it with the team using the overhead projector. So they gather in the meeting room. He turns the projector on. He puts the first transparency on the glass, and he looks at the screen. Everything's out of focus. But these things take a while to warm up. So he decides to just wait for a few minutes and let the projector warm up, see if that makes a difference. And he looks, and it's still out of focus. He fiddles with the knobs to try and get the focus right. Nothing works. And it's so out of focus that it's literally unreadable. So at this point, Mickey's frustrated and pretty embarrassed in front of his team. And so he storms out of the room, immediately goes over, writes up a purchase order to buy a new projector for this room, throws it on his supervisor's desk, and storms out because he's convinced that his request is going to be denied. He figures they're going to say, you know, Mickey, there are other projectors you can use. You can use a different conference room. And his thought, and I agree with him, is that, you know, if the organization is asking me to work on improvements, they need to give me the right tools to do those improvements. They give me the tools to fix broken equipment. But if they want me to make improvements, they need to provide the tools necessary for making improvements. And in this case, an overhead projector was one of those things. Well, much to Mickey's surprise, his supervisor did approve the purchase order. And so the projector was purchased. It came in a few weeks later, was set up in the conference room. And so then Mickey and his team were able to reconvene and start working on the original project. So he was able to put his data up there. They came up with a good solution, went out in the field and implemented it, got back together in a couple of weeks just to review the results to see how they had done. And they were pretty excited about the improvement that they had accomplished. And then one of the team members said, you know, I've been thinking about these defects, and there's another one out there. And I think it's another opportunity for improvement that I'd like to work on. And I'd love if you guys would work with me and help me out on it. They said, sure. They took that project on. They got that one done. They met again to review the results. And somebody else said, there's another project that I think we could work on. And then there was another one and another one and another one. So over the course of 15 months, while still doing their regular job, this one small team, I think they had 5 or 6 people on it, was able to identify 157 defects that they felt like they could make an improvement on. And during that same time period, they eliminated almost half of them. They were still working on the remaining half, but just getting half of those 157 done, this team was able to save $1.8 million. And it all started by eliminating the defect of the faulty overhead projector. So with defect elimination, you tap into a wealth of knowledge by engaging many eyes, many hands, and most importantly, many brains, not just the reliability people. So eliminating defects at their source is the key to breaking the reactive cycle of fail, fix, repeat. But it's not something the reliability team or the engineers or even the entire maintenance department can do alone. It's definitely a team sport that requires participation from everybody in the organization. And I would say that includes from senior leadership to the front line, from maintenance to operations to procurement to finance, HR, marketing. Everybody that has a chance to put defects into the system, if not directly into the equipment. And so if everybody's putting defects in, we need everybody's help in stopping them from coming in the first place. Working together and armed with the knowledge about the sources of defects and a don't just fix it, improve it mentality, defect elimination teams can turn the tide of defects. Now, just because it's a simple process doesn't mean that it's going to be easy to do. It's not a miracle cure. It's not going to happen overnight. But much like building a protective wall brick by brick, or in this case, bug by bug, defect elimination teams can put an end to the churn of the reactive mode. Making work go away is what defect elimination is all about. All right, so that's my information on defect elimination and how to use it to break the reactive cycle. I've got some information here, my contact information, my email's on there. I've got a QR code for my email and my LinkedIn account. You can also contact me through the conference app. I'm checking messages there. With the limited time today, I'm not able to really get into the details of a defect elimination process, but we do have a book that we've written about it called Don't Just Fix It, Improve It. It's a really easy read written in story form, and it's available on Amazon. So I've got the QR code there if anybody's interested in learning more that way. All right, so now what questions do you have for me?
Right now, I'm looking at the chat. At the moment, I don't see a particular question brought up just yet.
Okay.
But I will wait here for a few minutes. I also deal with these aspects of defects, and increasingly, I also notice it in things having to do with processes that are, let's say, all the way from when there is a work order created, right? That so just sort of the handoff that is increasingly electronic between team members, and sometimes those processes can really just really create a lot of problems because the wrong things get ordered, or the wrong timing, the wrong terms, etc. Any further comments about that, Michelle?
Yeah, I think that all of the electronics that we use now can certainly make things better in some ways, but they also can create some issues for us. And so I think part of what we really encourage with defect elimination is this idea of kind of taking personal responsibility to making sure that you're walking things through the system. So don't just write the work order and walk away. If you don't get an answer about it, then pursue it. Go ask somebody, because sometimes things just fall into that electronic black hole through nobody's fault, or again, the wrong parts get ordered. We really push people to say, just don't accept that. Make sure you're intervening and making sure you get the things you need in order to do the work.
I think one area where it's ripe for this, things like inventory control. It's amazing. You would imagine things come in, things leave out, and it should be perfectly balanced. But in my experience, it just never really quite match. It's just keep looking for why is this happening, and it's always an issue. And we always are making some incremental changes that are improving, but then still it's just not been able to really solve that mystery.
Yeah, it should be simple math, right? You have what you have, you add, you subtract. Some of this, I think, is the nature of the reactive mode, though, that what I find mechanics do is they tend to hoard parts. The first time you stock out on something, maybe you need one the next time, but you go ahead and get two, and you stick one somewhere where you know where it is, so that you're not going to lose track of it. And I think sometimes that starts messing with the system, that you start losing count because you have a lot of sort of secret stores kept in little cubbies all around the site.
Here, somebody share a thought. Most companies become scientific with their reactive cycle by employing PDM tools.
Interesting. I'd like to know more about what they're saying there. They become more scientific with their reactive cycle. And I'm not sure if this is what the person's specifically talking about. But one of the things that I've seen with predictive technologies is that some organizations feel like that's going to be the answer. And so if we just can predict what's going on, then it's all good. Well, that tells you where the problem is. That doesn't actually fix the problem. And so I've heard somebody else refer to it as high-tech run to failure. So we know that we've got an issue. We then ignore that issue and the equipment fails. I'm not sure if that's what's being talked about there, or trying to use PDM to get out of the reactive mode. If you're using PDM properly, then it certainly should help you get out of the reactive mode.
Yeah. It reminds me a little bit of like ISO, right? You can be very good at making the wrong part.
That is exactly it. Exactly it.
Very, very reproducible. So
absolutely.
Any other comments? Many good comments about your book, by the way. So I think
nice.
here somebody shared, in fact, how
The
to get
link.
it and so on. So I think I'm going to look into it myself. So.
Yeah, it's a really easy read. And as I mentioned, it's written in story form. And so it really goes through because defect elimination itself is very simple, right? Find a defect, get a team together, do things to eliminate the defect at its source. But it's a challenge to get it implemented. And it's a challenge because of the people involved, because there's a history of a reactive way of working. And so the book really dives into kind of the human dynamic as well as the actual technical details of how to do it. And I've had a ton of people read the book, there are characters in there and they'll say, in the book, you call him Billy, but I know that guy. I've met him. His name isn't Billy. Mm-hmm. And so, people really identify with some of the roadblocks that you run into, some technical, but most of the roadblocks are human roadblocks.
Yeah, I think sometimes we identify the problem and then we don't actually act on it until it happens again, right? That's the other problem, that oh my God, and then there's lots of activity and then it dies down and then it's not actually fixed.
Yeah. And again, I think the nature of the reactive mode is you're so busy fighting those fires that you really don't have a whole lot of time to kind of finish it up and say, okay, now that we've solved this problem, let's make sure we update our procedures. Let's make sure we update our training. Let's update the part that we have in the storeroom. You just say, oof, I'm glad that's over. And you move on to the next fire that you have to fight. And I think that's getting out of that churn, breaking that cycle is an important part of improving reliability.
Mm-hmm. Very good. So I think we have reached the end. Thank you very much, Michelle. A pleasure.
Thank you so much.
And I hope everyone enjoys the rest of the presentations.
Yeah, I've been enjoying them as well. I'm looking forward to the next set.
Very good. Excellent. Thank you.
All right. If anybody has any questions, drop me a line.
Very good. Will do. Thank you.
Thank you.